welcome you all to this course on defects in material. Okay. Seeing the title, you will be thinking why this transformation in materials is being taught in this defects in material course, because Martensitic transformation has got lot of characteristics which are quite similar to twinning. That is why this transformation has been included as part of defects in material. Okay, especially the crystallography of the phase transformation is quite similar to twinning deformation or homogeneous deformation. Okay. Before we go further, let us look at what are the characteristics of the Martensitic transformation. The first thing which one should understand that this is a very important transformation which occurs in material, and this is the transformation through which the low carbon steels or most of the iron carbon steels could be hardened. There are various ways in which, maraging steels, there are many types of steels are there, trip, there are many steels which are ferritic martensitic steels. All of them employ Martensitic transformation to change the mechanical property of the material. Okay. The first thing about Martensitic transformation, let us first look at some of the characteristics and observations before we go into the crystallography. The first thing which had been seen is that if you take a sample, keep it at a very high temperature T1 and then quench it to a temperature T2, which is maybe room temperature, then the rate at which it is being quenched at is maybe around 10 to the power of 3 or 10 to the power of 4 okay, degree centigrade per minute or second, you can take it. Then what we are seeing it essentially is that when this quenching is very fast, okay, it undergoes a transformation, especially in iron, okay, from FCC to BCC. And what is essentially important is that when the sample is being seen, okay, some new phase which has formed in the grain, which looks like a needle or a plate shaped, and the size of the plate is so large that within very short time, if it is by diffusion, this plate has to grow, it is almost impossible. Okay. That means that this transformation essentially appears to be a diffusionless, or diffusion does not play any part. Okay. Then the other observation is that this region has completely transformed from FCC to a BCC or BCT. Okay. That means that the entire transformation from one phase to another phase has occurred, and it is like a single crystal of it. This whole region has transformed complete to the lattice has changed. That means that there is some systematic way in which this transformation is occurring. Okay. That means that it may be some sort of a shear induced or something which happens. So, this is called as something like a military transformation. In many books you will find the name that diffusional transformations are called as civilian transformation. Okay. Then what is the another observation? If you look at this region where the surface was initially flat, in this transformation there is some change of surface has occurred. That is, and not only that, the shape of the transforming region appears to be changing. Okay, from what it was, it has changed to another shape. Okay. These things could be observed using optical microscopy or atomic force microscopy could be used, okay, to look at the surface relief. Okay. In fact, this has been seen, that shows that there are a lot of distortions are occurring on the sample surface. Okay. So, on the basis of this information, the Martensitic transformation is defined as, okay, it is a distortive and diffusionless transformation. There is another word also used as displacive transformation. Okay. That is, atom is displaced from its position to another position, and the displacements are, if you look at it, less than lattice translation vector in most of the cases. Okay. As I mentioned, when we quench the sample up to a certain temperature, okay, there is no transformation, and when you quench below a temperature, this transformation starts. This temperature is called as, it is generally written as MS, that is Martensite start temperature, and then this transformation gets completed at some lower temperature called Martensite finish temperature. Okay. In between this temperature, if we cool it from one temperature to another temperature, okay, that is above the Martensite start temperature, we start, take it to a temperature which is in between some temperature, you take it to be T3 in between these two temperatures. And if you hold at that temperature and look at that sample, the volume fraction of the martensite which has formed remains constant. That is, keeping at that temperature for a long period of time, there is no change in the volume fraction. That means that this has nothing to do with, this is also another indication that this has nothing to do with the diffusion which is occurring, nothing to do with diffusion. Okay, there are some other martensites which are there, those part of it, because this is not a course on martensitic transformation. So, the subtleties, various subtleties regarding this transformation we will not go into it, but we will talk only about the general characteristics. Okay. Essentially, it is called as an athermal transformation, that means which does not depend upon the temperature. Okay. Yeah.
It will end up with MF or
with MF. MF it should complete itself.
If it hold in between MS and MF.
MS and MF, some volume fraction is formed. Okay. That is proportional to, that is, here it is 0% of martensite. Okay. And here it is supposed to be 100% martensite. In between, the volume fraction will vary from 0 to 100%. Okay. What are the other characteristics by which martensitic transformation could be understood? Okay. Suppose we take a sample, we wanted to do some heat treatment which is supposed to undergo a martensitic transformation. We polish the surface of the sample, okay. Then allow it to undergo a martensitic transformation, keep it at a high temperature, then quench it quickly, okay. Assume that essentially a plate type of a martensite forms. Then the first thing what has been observed in this sample is that when such a transformation is occurring, if this is the sample which is a very polished sample, assume that a single plate has formed, then it is seen that this plate essentially forms with some two very sharp interfaces. Okay. That is the first thing which can be seen. Okay. Then another one is, if you look at it from the side, that is where we are seeing it, there is a relief which is being seen on the surface, correct? This is the second observation which we can have. Okay. And since the relief is being seen and this line is very sharp, that means that this looks like typical of twinning. Twinning also, the similar type of a behavior is noticed. Then it was thought that can we apply the twinning theory to explain martensitic transformation. Okay. That was the whole assumption on which this whole martensitic transformation theory was developed. Okay. Then another one, what we have to do it is that, suppose in this sample, before this transformation has started, this is a sample which is a plane, we can see a surface which is very sharp. Okay. Suppose in this sample, before the transformation, we assume that we have drawn a line like this, that is, a scratch has been made on the sample surface. Then the sample is allowed to undergo transformation. Then what happens is that after the transformation, one could see that this line remains straight up to here. From here to here, it is again remaining straight, though it is changed direction, then it goes straight again. That means that tuning also exactly the same thing happens. That means that the deformation appears to be continuously a homogeneous deformation which is occurring parallel to this interface possibly, correct? That is one of the surmise which we can make looking at this microstructure, correct? And similarly, whenever twinning occurs, if you do a test, we can see a noise which is called click, 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 it will come, the sound will come. Okay, when you do a mechanical testing, you can see that. Similar to this, when a Martensitic transformation also, if you do especially stress induced or strain induced, you can hear the same thing. So, all these observations are very similar to that of when a twinning occurs. Okay. That is why it was thought that whether we can apply the same theory. Okay. That means that the question which arises is that twinning we explain on the basis of a homogeneous shear. Okay. Can this be done using a homogeneous shear to transform from one lattice to another with the extent of surface relief or the macroscopic strain which we are seeing it? Okay. Is it possible or not? The answer is no, but this we will see it the course of the lecture. Okay. Why it is so? Okay. So, as I mentioned, we are considering a sample which has transformed. Okay. The lines have been drawn and we see that the lines have been tilted. Okay. If you look at this sample in an optical microscope, when these lines are very straight, if it is a single crystal, we can find out what is the orientation plane of the faces which are connecting these two. Okay. On this side as this way, this is called as the habit plane. Okay. That is the plane in which the martensite and the parent face are joined together. Okay. If we do an electron microscopy from this sample, okay, then I can find out the orientation relationship between the martensite and the parent and find out which directions match with which directions. All this information we can get it. Okay. Then as I mentioned, since this line is a quite straight, that means that deformation could be a homogeneous deformation. Okay. And the third is, if you look here, this line is straight up to the interface. That means that whatever the deformation which this region has undergone, okay, there is no semblance of any effect strain on that other side. As if this region remains straight up to this, just the other region transforms, and here again we do not see it, correct? The effect of the transformation does not affect adjacent neighboring areas in the matrix. Okay. Then this continuity, if you look at it, this is just joined here. That means that there may be a continuity between these planes which are joined together. This, and that means this plane could be an undistorted and unrotated plane. Okay. So, any strain which leaves a certain plane unrotated and undistorted, okay, we call such strains as invariant plane strain. Okay. That is the definition. Okay. As I mentioned, can this strain be applied homogeneously to transform the matrix to the martensitic structure? It is no. Okay. That is because a strain which is required to transform homogeneously from matrix to the, that is matrix lattice to the martensite lattice. Okay. But there is another strain which we are seeing, it macroscopic strain. Okay. Both of them are not that same. That we can understand from this figure. Okay. Essentially here what we have done it is, you take a two-dimensional square lattice, okay, allow it to undergo a transformation, okay, that is homogeneous shear. If we apply, it undergoes a transformation to the structure. What is happening is, suppose we have this is the that is essentially a square cell has gone into a parallelogram. A phase transformation has occurred. And what is the strain which will be corresponding to this? This is going to be the displacement. Okay. This you can take it to be the shear if you know this angle from which tan theta will be the shear which it will be giving. This is the shear which is required to transform from one lattice to the another lattice, correct? Once this transformation has taken place, there is a lot of shape changes occurred. Okay. If we introduce in this lattice, okay, either some slip in this lattice which it occurs, slip by moment of dislocations occurs in this direction, okay, that can change now the lattice structure from here to, this is the shape which was originally it was there. Now we assume that this is what it is. Like this, it undergoes a change. Now if you look at it, this turns out to be the external surface. Okay. This is called as a lattice invariant shear. What we are doing it is, that means that lattice invariant shear means that this shear does not change the crystal structure, but essentially a shape change it is occurring. Now if we look at with respect to this direction, essentially the strain which we see, the shape strain, is very small. This is the observable strain which we are seeing during the Martensitic transformation. Okay. So if we see this particular structure, whether it corresponds to just a simple homogeneous shear, no. A homogeneous shear has transformed it. Then what we are seeing it is that we have introduced the lattice invariant shear. This could be a slip which we have considered, otherwise it could be a twin as well. So twinning means that so this sort of a, that is, it transforms by twinning. When we transform by twinning, it has the same crystal structure but in a different orientation. Okay. So these are all the two ways in which this transformation could occur. Both the types of transformations have been observed. Generally these type of ones which we see, call it as lath martensite morphology. These are called as plate martensite or twinned martensite. Okay. So essentially crux essentially of this Martensitic transformation, crystallography of Martensitic transformation, how we can consider is that there is a homogeneous lattice invariant shear, homogeneous deformation by which we transform from the parent to the product lattice. Afterwards we introduce, okay, a local deformation which we call it as lattice invariant shear, with which we can change the, try to bring back to the original shape as possible. Whatever is the portion which remains, which has not been accommodated, that strain, that is what we see as the macroscopic shear. This strain also, if we look at it, looks like a homogeneous one. Okay. That is what is being observed in the sample. Okay. Here what we have done, we have just postulated that this is one way in which this transformation could occur. Okay. Experimental observations, what we have, we know the crystal structure of the sample initially, what is the crystal structure afterwards. Okay. We can find out from experimental observation what is the habit plane in which it is lying, what is the orientation relationship, what is the crystal structure of the parent and the product, what is the orientation relationship. These are all the observations. With this theory, which is essentially a homogeneous shear or homogeneous deformation, we should try to find out, okay, what will be the shape change which should occur, whether the macroscopic strain, the orientation relationship, okay, all these things could be predicted by the theory or not. If this theory is able to predict it, we can say that okay, this is able to explain the experimental observation. But this is called as a phenomenological theory, because what is the path which it is taking during this transformation? We do not know. We have only that initial state and the final state. We know that. We are trying to put forward theory. This is the way this transformation might have occurred to reach this final state. Correct? Yeah. So, this is essentially what I had shown in this transformation. So, here what has been done is that inside the square a two-dimensional small lattice is also being shown. Okay, that square lattice, it transforms to a parallelogram, and the same thing could have been achieved. Okay, this shape change could have been achieved through a slip taking place homogeneously in the material. But though the shape change has taken place, the crystal structure has not undergone any transformation. Correct? That means that this is not a Martensitic transformation. But once this shape change has taken place, as I mentioned, either by slip within the transformed lattice or by twinning within the transformed lattice, we can try to bring it back as close as possible, okay, to the original shape. Whatever is the remaining strain is what it comes as the macroscopic strain which we are seeing it. Okay. We will look at it how this macroscopic strain is accommodated. That is also very important. Okay. Okay. This I have already explained. Okay. Here I had shown the same thing which I have done. It is a lattice which is a square lattice. We assume that this region undergoes a Martensitic transformation. Assume I cut it out, allow it to undergo a Martensitic transformation. It has undergone a shape change. Then introduce slip into it to bring it back to the original shape, as close as possible to the original shape. Okay. If I try to introduce this into this lattice, what I should do? Normally, I should just apply some surface tractions so that the shape is brought back exactly to this shape and introduce into it. Once it is introduced into it, then you allow it to relax. When we allow it to relax, the part of the matrix and this transformed phase both will take care of the strain, correct? That is how it will be accommodated. But in the experiment which we mentioned, the lines, if we look at it, right up to this point, okay, there is no change in line. That means that there is no strain is getting accommodated. So, what is the only way it can happen then is that you just rotate this as such like this, okay, so that it matches with this shape, and try to fit it at this interface where it has been cut, okay, which is the habit plane. Then it is in a rotated shape. The other portion also connected like this, because when it has been initially cut, it has been connected parallel to these two lines. So, this now if you look at it, there is a surface relief has come. So, essentially this rotation is what you are seeing, it is just the surface relief, because that is also a part of a strain only, correct. So, that is what we are observing it as a macroscopic strain, or the macroscopic surface relief which we are seeing it is this change. Is it clear? Okay. So, this red line which I have drawn is the habit plane which is joining these two faces. Okay. This habit plane could be a high index plane. Okay. This we will shortly look into it, how to find out these habit planes. Okay. The crystallographic theory we will cut. Okay. Before we go further, let us recapitulate, because we are talking about this transformation, and as I mentioned so many times, homogeneous shear which is taking place in this material. Let us look at the characteristics of a homogeneous shear before we go into the Martensitic transformation theory. Okay. Suppose a simple shear is one in which, okay, in only one direction a shear strain is being applied. What we have taken is essentially take a hemispherical sample of the material where we apply a simple shear, okay, G is being applied. Then what it will happen is that this will transform into a elliptical shape, because only one direction the shear is being applied. So when the shear is being applied, the matrix can be written in this particular form. Okay. So G is the simple shear strain, correct? So essentially what is going to happen is that if this is the origin of the coordinate system, okay, it has been each of these points on the surface by the simple shear gets transformed to a corresponding point like this, correct? This is how the transformation is occurring. That means that suppose I look here, this is the original vector from here to here. Now that has transformed into another vector, which essentially has its length has been shortened. That means that most of the lines are undergoing a distortion. But there is one particular line which essentially the magnitude from here it has come to this one, which has not undergone any transformation. Okay. This is this is rotated but not distorted. Okay. Since we are considering only a simple shear in this direction, perpendicular to it, if I look at it, okay, there is no change. Okay. So there is a plane which is passing through these directions. Okay. That plane is a unrotated, that is rotated but distorted, undistorted plane. Rotated and also undistorted. Whereas since we have held it here, here the strain will be 0, correct? Shear strain. This is the plane which is unrotated and undistorted. Okay. This plane in twinning morphology we call it as K1 plane. The plane which contains here is called as K2 plane. This direction is called as eta 2. The direction here is called as eta 1. Okay. This you are familiar with it. Recently only we have had lectures on these aspects, correct? So this is one characteristic, that is the plane gets rotated or distorted. This is because the same transformation, okay, we could consider it in a different way. That is, this is how the strain tensor we are writing it, correct? This itself could be written as equal to correct. This is a pure shear, okay. This is a rotation, shear, rotation, and this is, we call it as a simple shear. This is what essential. So simple shear consists of a pure shear plus a rotation. And we know that if pure shear is being applied, this is equivalent to, that's or applied, we can find out some principal strains in which the shear component becomes 0. That is, only principal strains are there, which is pure strain, correct? That means that the pure strain is essentially will be that in tension in one direction and compression in another direction. Okay. These axes generally, when the strain is small, is at 45 degrees with respect to the axis in which the shear strain is being applied. Okay. Then we will be able to write this into another strain, which is written as what is K here essentially is nothing but the total extension which we see in a unit length of a sample. Okay. So, k minus 1 gives the strain part of it. Okay. Is this clear? So, essentially what we can consider it is that by giving a strain, this can be written as something which is similar to in this, which can be written in this form, that is something like because so that the total, when shape change does not take place, the sum of the diagonal elements has to be 0, correct? So, in this form we can write it. So, essentially what is required is that a simple shear is equivalent to considering a tension in one direction and compression in another direction, okay, along principal strain directions, okay. And then if we give an appropriate rotation also corresponding to this one, we can bring back to this original shape, correct? This is clear? So, the simple shear is equivalent to both the ways we can consider it. So, simple shear can be considered as giving pure shear in two directions, and that is this. If you remember, I had shown that if you consider a square, if you apply a pure shear, this will change its shape to this particular shape, correct? And then if we give a rotation, it will be coming back to the shape like this, like a simple shear. Okay. Now, the same shape could be achieved by taking the square and pulling it in this direction and compressing it in this direction also, it could be done. Okay. Why we considered this? The reason is very simple, that in most of the Martensitic transformation, when a crystal structure goes from one structure to another structure, by pulling in some direction and compressing in some directions to the unit cell, we can make the requisite shape change. Okay. That shape change can be considered as equivalent to, that is, if we can transform it to some way where it resembles like this sort of a strain matrix, okay, then the same theory could be applied, the homogeneous deformation theory could be applied. Okay. Only a rotation has to be given to bring it back to the original shape. Okay. So, this is exactly what is being done, is that the same thing could be, that is what I had shown here. This is the sphere of the original sample, and we have pulled in these directions. It has undergone a transformation, and this is how it looks like. Okay. And this can be written as equivalent to, this is the way it is, okay, plus a rotation will be required. Now, we will find out how we go about and give these distortions to the sample to get the requisite changes to the parent lattice, so that we are able to generate the Martensitic structure. Okay. Let us now, what you have to remember here is that the simple shear is equivalent to essentially a tension and compression in directions which distorts the shape, and a rotation which is required to bring it back to the transformed stage. Okay. That is essentially what is, which will be employing in this analysis. Okay. Let us consider some specific cases. Okay. One, Martensitic transformation in cobalt, let us consider. Because cobalt is at high temperature, it is hexagonal closed pack. It transforms to face-centered closed pack. Okay. That face-centered cubic lattice, okay, at lower temperatures below 420 degrees centigrade. So, above 420 degrees centigrade, it transforms to HCP. Okay. What is the stacking sequence in these lattices? Okay. It is essentially ABC, ABC is the stacking sequence in FCC, AB, AB, AB is the stacking sequence in hexagonal closed stack. Okay. Suppose I introduce a stacking fault in this lattice, okay, at any plane. Suppose we assume that in this direction we are introducing a stacking fault, we are introducing a stacking fault here, then it will become ABC, ABC, AB, C goes into A, okay, A goes into B, then this is C, ABC, this is how the stacking sequence becomes. So, we have an AB, AB type of a stacking sequence which has come. Okay. Now, if I introduce a stacking fault again here, that is here we have introduced here, that is the transformation is from here, now we are leaving one and an alternate layer we are doing it, then what it will happen? ABC, ABC, AB, AB, this C will become A, this will become B, ABC, right. So, now you see that the thickness of the HCP is increasing. But what one should remember here is that this is done through introducing stacking fault in every alternate layers, okay, not on every consecutive layer. If we introduce stacking fault in every consecutive layer, we form a twin of the FCC lattice, but on every alternate layer if we do it, okay, we can increase the thickness of the HCP lattice. Okay. That is what essentially is being shown. No, no, that depends upon the temperature, chemical free energy change which is going to take place. Okay. That is, even if when we generate one defect, that is one partial passes through a plane, it is generating here a stacking sequence which is AB, AB has come. That means that a nuclei of HCP has already formed. Okay. But if it has to grow, it all depends upon what sort of a free energy change which is available when it goes from one phase to another phase transformation. The thermodynamic equilibrium phase change, if it has to occur, the free energy change also should be favorable. Okay. Then otherwise it will be only just remaining as a fault. It will not grow into that phase. Okay. So, here the FCC we are doing at every two layers, if we introduce a stacking fault, okay, then essentially we have transformed this into an AB type hexagonal lattice, correct. What will be the shear which will be associated with this sort of transformation, because it is not in one layer, it is over two layer. So, the shear will turn out to be √2/4, it is a simple shear which is occurring, but the value of this shear will be, in the case of twinning and every layer when it occurs, we found that the twinning shear in FCC is 0.707. This value will turn out to be, for HCP, this should be every alternate layer, means that the shear will turn out to be 0.35, half of that shear. This will be the twinning shear which is required. Okay. And another is the plane over which these layers, the FCC and the HCP meet is along 111 plane of FCC parallel to 001 plane of HCP. So, that becomes the habit plane. Okay. But this involves a lot of shape change which has happened. Instead, if on some layers it is in this direction, and we have studied earlier that whenever atomic movement takes place in a hexagonal closed packed plane, okay, let us consider a two-dimensional hexagonal lattice. An atom sitting, if this is an A position, this is B position, this is a C position. So, from this C position, okay, any movement which takes place either in this direction or in this direction, the partial movement, it all takes to B position, correct. So, it does not matter which is the shear vector which is being used. So, instead of B equals 1 by 6 1 bar 1 bar 2 on 1 on 1 plane, if B equals 1 by 6 to 1 bar 1 direction we give a shift, that will also create AB type of a stacking sequence. That means that the HCP lattice is being done. But if you look at the amount of displacement which is occurring in each of this direction, they turn out to be very small. So, that is what essentially we can see that nearly the same shape is being maintained here. Okay. So, the macroscopic strain which we are seeing, it is going to be negligible in this case. Okay. In fact, experimental observation is that this is indeed so. Okay. But what we should understand is that suppose we try to give a homogeneous shear, because we said that this is the shear which is simple shear which is required. But if the shear is given homogeneously to the entire atom, every alternate layer atoms will become to a correct position, but in between layer will not be brought to, because it will be half of that shear which will be given. So, it will be shifted to position. So, as I mentioned, like in twinning, some shuffles will be required to bring them to the correct position. Okay. That is what possibly might be occurring. All right. So, with that shuffle, a complete structural change would take place. Okay. These are some experimental observations. Okay. Is that the same thing in cobalt with some alloying addition? I think nickel has been added to stabilize this FCC phase, so that part of the FCC phase remains during the transformation. Okay. This is the transformed region which is an HCP. Okay. If you look at these lines which are there, these striations, these are all one on one corresponding to intersection of one on one planes with the surface. Okay. Then between closed packed planes and closed packed directions, okay, from electron microscopy or X-ray diffraction, try to find out what is the orientation relationship. It has been seen that the planes and directions are within plus minus half a degree. They have been precisely measured. Okay. That is what it has been observed. Okay. Then in these sort of sample, when an atom probe microscopy is taken, one can see that there are some steps which are occurring. Not atom probe, atomic force microscopy. When we look at it, atomic force microscopy will give the depth information, how the height varies. So, we can see that there is some variation in height which is occurring. This variation in height could correspond to here. If I take and probe across it, you find that there are some height changes which are going to take place. This is exactly what it is showing. So, some region has shifted in one way, another region has shifted in another way. So, it looks like a corrugated structure, correct? Okay. And people have tried to calculate what is the, whether there is any volume change which is taking place, because atoms are shifted from one position to another position and it takes place over a second layer. A small change in volume has been noticed, and this change is about 3.6 into 10 to the power of minus 3. Okay. This is what essentially.
Lattice parameter does not change. There shouldn't be any change in volume.
Which one? The C axis will change a little bit.
Distorted.
Yeah, slight change will take place. That is what it gives to a small change in volume. Okay. Okay. Let us consider another case, which is essentially a transformation from BCC to HCP. Okay. zirconium, titanium, all this material at high temperature it is BCC. They transform to NHCP at lower temperatures. Okay. And this transformation essentially occurs martensitically. Okay. How can we view this change from BCC to HCP? Okay. The way we mentioned, first let us consider a unit cell of BCC, okay, and then we will apply some shear transformation to change it from BCC to HCP, a homogeneous lattice shear which we are giving it to transform it. Okay. So, for that the unit cell which is being chosen is such that it contains, it is a non-primitive, contains 2 atoms per unit cell, because HCP also contains 2 atoms per unit cell. Okay. It is chosen in such a way that this is 100 direction, this is 011 bar direction, this is 001 bar direction. This is how this unit cell looks like. To this unit cell, okay, if I give some distortion, elongate it in one direction, compress it in another direction and elongate it maybe in another direction, I can, by introducing these shape changes, we can transform it to any shape which we want. So, these changes back are these changes to the hexagonal unit cell. Okay. To achieve this, the type of strains which are required is in this direction a 10% contraction is required, that is along 100, 10% expansion is given along 011 bar direction and a 2% expansion along 011 direction. This is all with respect to a BCC lattice. Okay. Since it has transformed to an HCP, now we know that what is the, we can find out the orientation relationship also, that is 011 of beta corresponds to the basal plane of alpha, it has become this plane because it is perpendicular to this direction. Okay. And then the direction 11 bar, 2 close packed directions are there, that has transformed to 112 bar 0, and this third direction has transformed to another 110. So, essentially all the 3 close packed directions of hexagonal lattice has been generated in this structure this way. Okay. And we can choose any type of a lattice, that is whether this sort of a unit cell has to be chosen, or can we not choose in BCC any other type of a unit cell and try to applying shear we can transform it to this particular cell. It is possible always, but the thing is that we choose a cell which requires minimum distortion. Okay. By giving minimum strain we can transform it, that is what we have chosen. And when we give strain in this direction, this strain is uniformly applied. So, it is a to the unit cell throughout the lattice it is being applied. So, it is a homogeneous deformation which is taking place, correct. Okay. And another is that we have studied earlier that when we have given such strain and deformed from one lattice to another lattice, we can using the lattice correspondence we can find out the directions and planes corresponding to the same direction in each of the lattices. That is what essentially the matrix corresponding that is given. What is the strain matrix here? The strain matrix now it turns out to be in terms of the BCC is 0.1, 0, 0, 0, this is 0, 2. This is exactly what it is. Okay. Now, if we look at this strain matrix, this is positive, this is negative, this is a very small value. Okay. How this shape change can be represented? This shape change can be represented, that means that this should become an ellipsoid of revolution, correct. So, essentially an ellipsoid of revolution, that is Suppose we take a portion of a sample which is a sphere, okay, with the orientations which we have chosen, and then try to give the respective elongations 10% in two directions and 2% in other direction, so that it has become an ellipsoid, correct? And if we try to join both of them together, that is superimpose, not join, superimpose one on top of the other, we will find that there is some vector around which the sphere and the ellipse meet. That means that in those directions the magnitude of the vector remains that same. Okay. If we try to look at the locus of that, that will turn out to be a circle on the surface, two circles, okay, and this will be joined by to the center. If you see, it is something like a cone. Okay. That means that for a simple shear what we have considered, or homogeneous shear, simple shear which we have considered, there is a plane, correct? For that plane to be generated, if we are applying strains along principal directions, one direction contraction, one direction expansion if we give it, keeping the volume constant, then that plus a rotation can be equivalent to a simple shear, so that a plane which is unrotated and undistorted will come. But that will not happen here. If this has to happen, what we have to do is that in the strain matrix, the one strain which is there, do something, apply some deformation to it locally, so that the strain is compensated. That becomes 0. In this particular case, what is essentially is being done is that since the magnitude is very small, an approximation is being done, okay, that it is so small that it is negligible. Okay. We can go ahead with that. That is the way it is. Otherwise, how that accommodation is done? By either slip which is taking place in the sample, or a lattice invariant shear which is a twinning also can compensate for that, so that that component can be made 0. Then the strain matrix will now can be changed to right. Once it has been changed to this form, okay, it is very easy to handle. Okay. That is essentially what is being given, mentioned here. 2% strain is small compared to other axis, taken to be approximately 0. Okay. Then the necessary sufficient condition for there to be an undistorted plane is that one of the principal strains are 0 and the other two are of opposite sign. That we are able to achieve. Okay. How that one strain is being made 0? It is by lattice invariant shear, which we can add by either slip or twinning. Okay. Once that has been done, now if we look at it, we have, instead of a cone, there are two planes or circles which are intersecting each other, correct? This is essentially what is happening. Now you see that there are two planes which are there. Okay. This plane will be inclined at some angle with respect to these coordinates, and this is, we are marking all with respect to a coordinate system of the unit cell of the BCC which we have chosen. Okay. Right. And this brings out two planes. By rotating one of the plane, we can bring it to a position which is unrotated and undistorted. How we do it? We will just look at it now. Okay. You take this case. Okay. This is a part of cross section of a sphere which is a circle. This is the coordinate system. Okay. This one I had given some elongation, that is compression and tension. So, the volume is kept constant. It has reached this shape. When I superimpose, these are all the vectors where they remain the same, but where from this vector has come, when I have compressed it in this direction and expanded it in this direction, some point which is here on this, that has rotated and moved and shifted and come here. That is why it appears that same, right? In the deformed lattice, that is in the ellipse, a point which is there on the sphere, when it has undergone some compression and tension, has moved from this point to this point. That is why they appear as the same. That is what essentially is being shown in this figure. Now this is very clear. Okay. In this is the original point from which we have started. Now it has rotated and reached here. Suppose I give a rotation in this direction to this one, that is the whole, this deformed one. If I rotate it, this point will come back to this original position and join. When that joins, what I am showing it with the green line is the original position of this one. Now when this is being rotated, this also gets rotated and comes here now, and that has reached here. That means that this plane has become a unrotated and undistorted plane, because they are joined together, correct? And the plane which was there originally here has been rotated and has come here, because the magnitude of the vectors on this plane remains that same. So this is equivalent to a simple shear. That is exactly what now I have, just showing it, keeping this plane, rotating this and just showing it. So essentially, with the set of these figures, you can understand that how we can make a habit plane which is rotated, unrotated as well as undistorted. Okay. That means that after giving this transformation, some rotation also has to be added. That rotation is also dictated by the shear strain, correct? So here now if you look at it in this particular one, exactly the same thing which I had shown here. Okay. That is, one is this vector which has essentially rotated and come here. So this is the sort of a rotation which has to be given to join. Since we know this is the common point, what is the coordinate of this one, because this point is on the circle, correct, q dash, which is its coordinates are nothing but, essentially we can write x squared plus y squared equals r squared if you know x and y value. Similarly, this point which is going to be here has come from displacement from here to this one. Suppose this is x and y. Okay. Using the strain matrix, we can find out ux and uy and uz we can find out. That value turns out to be this one, okay, minus 0.1x and minus that is uy equals 0.1y. Okay. And since the magnitude remains that same, here also x squared plus y squared should be equal to the same as this magnitude. So we equate this and we can find out the ratio of x by y. The ratio of x by y will be tan inverse this angle which it makes from here to here. Now we know what is the angle at which this plane is lying, and since we know this direction and since we know this direction, we can immediately find out what is the direction in which this vector is lying and the plane which is contained in it. Okay. Since the displacements are very small, here this angle turns out to be around 46.5 degrees. Okay. And this plane, when it has been found out, that value turns out to be some 4/33. Okay. This is a high index plane. Okay. Is it clear? This is how we can essentially, because the habit plane is the one which is unrotated and undistorted, this rotation has to be given to this one to bring it to the original one. Okay. That rotation is what it appears as the strain. The macroscopic strain which we observe is that particular one. That is what essentially is being shown here in a crystallographic way. That is, a cross section of the lattice is being shown. Okay. this is 0 1 plane of BCC, okay, and this is what is allowed to transform to hexagonal lattice, okay, by whatever is the transformation matrix which we have discussed now, the crystallography, we allow it to transform. After this has transformed, okay, there is a slight orientation might have taken place, and when we try to fix it here, okay, we have to match the planes, match it. To match it, this has to be rotated a little bit and matched, and this, if you look at it, if you draw a line, this is what the rotational strain is. Okay. The rotation also is considered as part of a strain, that is, if a matrix cannot accommodate a strain by deformation, it will try to rotate, correct. So, that is what essentially is happening in this case, okay. And now we can see what all the directions, these are all the directions. This is 0 1 1 of beta is parallel to 0 0 1 of 0 0 0 1 of alpha basal plane, okay. 1 0 0 of beta, okay. Since some small rotation has been given to accommodate this at the interface, so that the plane remains an unrotated, undistorted plane, because that has to be joined together, correct. Then this direction 2 1 bar 0 of alpha is rotated from this direction by about 3 degree. 1 1 direction of beta, the other direction which is parallel to a close pack direction, nearly parallel to close pack direction, it is rotated by 2.5 degrees. Okay. Then when orientation relationship has been found in these samples using TEM examination of these samples, when orientation relationship has been found out, it has been noticed that about 2 to 3 degree is the mismatch which can be found out between these orientations. Okay, that matches well, and the habit plane was found close to 4 bar 3 3 bar, and experimentally determined habit plane from analysis of micrographs also turn out to be the same value. Okay. That way now we can say that this sort of looking at analysis of Martensitic transformation, okay, matches very well with the prediction. Okay. So, that way it was decided that yes, this theory will work. Now, the next question comes is that there are many cases where the strain in the third direction is not negligible. For example, in the case of iron martensite. This case we will consider it in the next class. Okay. Next class we will take 1 or 2 cases, and how this is compensated, we will talk about it. Okay. We will stop here now.